Good afternoon, everyone. My name is Jason Allington. I'm the Vice President of Sales, and I've been involved in process air heating industry for about the last 18 years. So I'm going to go over the air delivery methods that we commonly use, and I'm going to go from a low efficiency zone to a high efficiency zone in that kind of order and work our way up. So the first type of zone is a quiescent zone or hot box, and it's one of the most basic types. And this type of zone has little to no impingement drying, and it is very quiet and has a little bit of very little heat transfer. It's often used to control the reaction on a web. The airflow in and out of the zone is controlled to maintain a specific set of conditions, mainly temperature, velocity, and humidity. It's got very low velocities of around 1,000 feet per minute. Some of these the applications that it's used for is for endothermic reactions, where a reaction on or within a web is giving off heat. This is seen in filter media often, and we're just looking to control the reaction and maintain it for a specific amount of time. It's also seen in wet bond laminates, where a coating between two webs or sheets is performing that reaction. The next step up from there would be a co-flow or counterflow zone. This can be controlled by a zone where you're delivering air on one side and taking it out on the other, or on an air bar to air bar basis, which is shown in the picture in the middle to the right. This type of zone has low impingement, and the nozzles can be close or far from the web. The nozzles or ducts direct the air mostly in the parallel plane of the web, and the web direction is independent of the airflow direction. Common air velocities for this are from 1 to 4,000 feet per minute. Because of the gentle nature of this type of zone, is often used for highly volatile solvents, where the product could be subject to surface defects if drying happens too fast. So the counterflow or co-flow zones limits the evaporation rate of those volatiles. This is seen with thicker PSAs and battery lines, which are just two very common lines where surface defects occur, where you get fish eyes, bubbles, scratches, and occurring from retained solvent. One of the most common types of dryers out there is the classic impingement dryer, and this utilizes hole bars or slot nozzles. The hole bars have a series of non-lined up holes. They're in a pattern so they don't cause streaking, whereas a slot nozzle has one or two slots that direct a jet of air across the entire width of the web direction. So these classic impingement dryers, where the air is directed perpendicular to the web, the nozzles are set up so that they can be moved close or far from the web, depending on how intense you want the impingement, and the web direction is independent of the nozzle orientation. Common web or air velocities for this types of systems are 3 to 7,000, but we're not limited to that. Like I said, this is pretty much a standard type of dryer, so it can be used for both volatile or aqueous solids or aqueous coatings. You'll see these on toll coaters, because they're required to run different products from across the converting industry. They're very versatile for general product selection, and the impingement nozzles are used when you want high or low velocity, but specifically directed perpendicular to the surface of the web. The next step up would be a single-sided flotation. Now, single-sided flotation can be located on the back side of the web, which you'll see it on the right middle picture. It's on the bottom side. It can also be on the other side since it operates like a airplane wing and actually sucks the web to it. The single-sided flotation nozzle or airfoil directs the air mostly parallel to the side of the web, which provides some energy input into it. It is a non-contact web support, so that carries the web through, that applies backside heating to drive out the solvent from the back, and you can select a variety of opposing nozzles. So that's what gives you the ability to adjust that energy input from very little to very high with this type of system, is selecting the correct nozzle that's on the opposite side. The air velocities are commonly but not limited to 4 to 10,000 feet per minute. The common uses for this type of nozzle would be on thicker aqueous coatings, medium to thick PSAs, and where no surface contact is required for product quality. That might be an optical film application or a very special tape. And it can, since it is a non-contact web support, it can be used on double-sided coatings and or on coatings where you have a backside adhesive that's been previously dried and you're rerunning the web with a new coating on the opposite side. Whereas if you put that over a roller, it may get stuck on that roller or have transfer of adhesive coating onto that roller. The double-sided flotation nozzle or Coanda nozzle has been around since the 80s, and it is a very standard nozzle for high energy input. The air is directed mainly towards the plane of the web, and it is a double-sided non-contact web support. Has a very stable flotation characteristics with this type of bar. The web direction, again, is independent of the nozzle orientation, and it has very high energy input into the web or coating. The air velocities, once again, are pretty much the same as the airfoil, from 4,000 to 10,000 feet per minute. This is most often used for double-sided coatings, very thick, heavy aqueous coatings, or heavy saturated webs. You can also be used for thinner volatile coatings that have high boilers, that you're not worried about them flashing off because it does have a very high energy input. You'll see this on this type of nozzle used on insulation layers for circuitry, where you're trying to drive off every last little bit of solvent within a thin coating. Now, along with all of those other types of nozzles, we can incorporate the use of IR heating. Now, they can be located, the IR heating emitters can be located opposing to or in between nozzles, and they are considered an independent zone since you can adjust either the intensity of the IR or the air temperature and velocity independently of one another. The wavelength on the IR can be selected to hit in a specific target energy input, and when this is in combination with the standard convection heating, it provides you the highest energy input into a Weber coating. The incorporation of IR heating into a traditional convection dryer allows you several things like it improves the energy efficiency of the overall drying system. It works really well with heavy saturated webs, high-speed applications, or systems where you are required to have a very small footprint. So where energy input into the web, high energy input into the web is of the utmost importance. We also use it as preheaters or post heaters for boosters, which allows you to run faster, increase your line speed, which expands your production capacity. And it can also be zoned across the web to improve the overall temperature consistency of your web leaving the drying systems. Now, this is just a quick reference graph of some of the most common applications. I've made this up to kind of as a speaking point years ago. Every year I do jobs that kind of deviate from this, but in general, this works pretty well when I'm looking at a new incoming system with a water-based silicone or a water-based adhesive. And I can use this as a talking point to help narrow down with a specific customer's process engineers. They might have, want to look at what, all the different types of coatings they have and how best are we going to design a single system to run all of those coatings. That's where it gets difficult, where you're trying to get multiple types of systems to fit in together.